The unseen ascent from gaming to global AI dominance, the architecture of an accident. The history of computing is often chronicled through the lens of Moore's law, the steady, predictable doubling of transistor density that fueled the rise of the central processing unit, CPU. Yet the most significant shift in computational power of the 21st century did not arise from the general-purpose CPU, but from a specialized component originally designed for a seemingly frivolous purpose, rendering video games. NVIDIA Corporation's transformation from a near-bankrupt graphics card vendor to the linchpin of the global artificial intelligence economy is a case study in strategic pivots, architectural risk-taking, and the cultivation of an ecosystem that existed for years before it had a commercially viable application. This report challenges the simplified narrative that NVIDIA merely got lucky with the AI boom. While the timing of the deep learning revolution in 2012 was indeed fortuitous, the infrastructure that enabled it, specifically the G80 architecture and the Cuda programming model, was the result of a high-stakes bet placed 6 years prior. This occurred during a period when GPU, general-purpose computing on graphics processing units, was a niche academic curiosity, barely recognized outside of specialized computer science departments. The ascent was not a linear trajectory, but a complex interplay of near failures, aggressive architectural decisions, and a willingness to subsidize scientific research for nearly a decade before seeing a return on investment. The following analysis is structured around the 3 distinct pillars that support NVIDIA's current dominance. First, the survival instinct, a corporate culture forged in the failure of the N1 and the liquidity crisis of 1997, which institutionalized a willingness to cannibalize existing product lines for performance gains. Second, the unified shader gamble, the architectural decision in 2006 to move away from fixed-function pipelines to unified shaders, the G80, effectively smuggling a supercomputer architecture into consumer gaming devices, a Trojan horse strategy that created a massive installed base for parallel computing. Third, the wilderness years, 2007 to 2012, a critical, often overlooked, half-decade where NVIDIA subsidized the scientific computing community, molecular dynamics, seismology, astrophysics, at the expense of its own margins, creating the software moat that would later capture the AI market.
The Precipice of Failure, 1993 to 1999. Founded in 1993 by Jensen Huang, Chris Malachowski, and Curtis Preem, NVIDIA entered a crowded market of over 24 graphics chip companies. The initial vision was not merely to accelerate graphics, but to redefine how computers handled multimedia. The founder set up shop in a modest office in Sunnyvale, California, with a vision that was as ambitious as it was technically risky. However, this ambition nearly destroyed the firm before it could truly begin. The company's first product, the NV1, launched in 1995, was technically innovative but strategically disastrous. Unlike the rest of the industry, which was coalescing around triangle-based polygon rendering, the standard that would eventually be cemented by Microsoft's Direct 3D, NVIDIA bet on quadratic texture mapping. QTM used curved surfaces to render 3D objects, theoretically allowing for smoother models with less data, a significant advantage in an era of limited memory and bandwidth. While elegant in theory, QTM was incompatible with the emerging standards of the gaming industry. When Microsoft released DirectX, it fundamentally relied on polygons. The NV1 was rendered obsolete almost overnight. Developers, forced to choose between the industry standard and NVIDIA's proprietary quadrilateral approach, abandoned the NV1. To compound the failure, the NV1 attempted to be a multimedia all-in-one solution, integrating audio and joystick control, which diluted its focus and added cost. The market rejection was absolute, software support evaporated, inventory sat unsold, and the company hemorrhaged cash. By mid-1997, NVIDIA was facing insolvency. The company had depleted its initial funding and had no viable product in a market now dominated by 3DFX Interactive and its Voodoo graphics add-on cards. The failure of the NV1 and the subsequent abandonment of the NV2 project left the company in a perilous position. Jensen Huang later recounted that the company was 30 days from going out of business. This moment became foundational to NVIDIA's corporate psyche, instilling a permanent sense of paranoia and urgency that persists even in its current trillion-dollar valuation era. Wang began internal presentations with those words for years, ensuring that complacency never took root within the engineering teams. Facing the abyss, NVIDIA executed a brutal pivot. They abandoned their proprietary QTM technology and the NV2, which was in development, and embraced the industry standard they had previously shunned, the triangle-based rendering pipeline. This required a complete re-engineering of their architecture in a frantic 6-month window. The decision was not just technical, but existential. They had to lay off staff and focus every remaining resource on a single product launch that would determine the company's survival.
The result of this desperate sprint was the Riva 128 released in August 1997. It was not the most feature-rich chip on the market, but it possessed two critical attributes. It was fast, and it was fully compatible with Direct 3D. The Riva 128 was the first high-performance 128-bit Direct 3D processor to render 2D and 3D images, marking a significant leap in capability for the consumer market. The Riva 128 saved the company. It sold 1 million units in 4 months, providing the capital to fund the next generation. More importantly, it established NVIDIA's operational doctrine, the 6-month product cycle. While competitors like 3DFX and ATI were on 12 to 18-month cycles, NVIDIA committed to releasing a new chip every 6 months, effectively doubling the performance of its products annually, twice the rate of Moore's Law. This aggressive cadence allowed NVIDIA to iterate rapidly, fixing bugs and adding features faster than any other player in the market. This relentless pace forced competitors to overextend themselves. By 1998, the release of the Riva TNT solidified NVIDIA's reputation. The TNT twin Texel engine could process 2 pixels per clock cycle, a significant advantage in the multi-texturing operations that were becoming common in games. In 1999, NVIDIA released the GeForce 256, which they marketed as the world's first GPU, graphics processing unit. This was not just marketing nomenclature, it signified a technical shift. The GeForce 256 integrated transform and lighting hardware directly onto the chip, offloading these complex geometric calculations from the CPU. Prior to the GeForce 256, the CPU was responsible for the geometry stage of the 3D pipeline, calculating the position of vertices in 3D space and determining how light interacted with them. The graphics card merely drew the pixels. By moving T and L to the GPU, NVIDIA freed up the CPU for game logic and AI, while simultaneously allowing for much more complex 3D scenes. The GeForce 256 could process 10 million polygons per second, a number that was transformative for game developers. The integration of T and L was the first step toward the GPU becoming a computational processor rather than just a pixel pusher. It demonstrated that specialized silicon could outperform general-purpose CPUs by orders of magnitude for specific, mathematically intensive tasks. This concept, specialization yielding massive throughput gains, would become the central thesis of NVIDIA's existence.
The Architectural Revolution, 2000 to 2006. Through the early 2000s, GPUs remained fixed-function devices. They had dedicated silicon for specific stages of the graphics pipeline. Vertex processors handled geometry, and pixel processors handled color and shading. This architecture was efficient for gaming, but rigid. If a scene had millions of triangles but simple lighting, the vertex processors would be overwhelmed while the pixel processors sat idle. Conversely, a scene with simple geometry but complex lighting effects would bottleneck the pixel processors while the vertex units remained underutilized. However, researchers began to notice the raw mathematical throughput of these devices. Early pioneers attempted to hijack the graphics pipeline for non-graphics tasks. a practice known as GPGPU, or General Purpose Computing on GPUs. To perform a mathematical calculation, a researcher effectively had to disguise their numbers as pixel colors, trick the GPU into rendering a screen, and then read the colors back as numerical results. This process was arduous. Researchers had to map their algorithms to graphics primitives like triangles and textures. Debugging was nearly impossible as there were no tools to inspect the internal state of the computation. Despite these hurdles, the performance gains were undeniable. For certain parallel tasks, even these hacked GPU implementations were significantly faster than the best CPUs available. This was akin to building a ship in a bottle, technically impressive, but excruciatingly difficult and unscalable. The inflection point for formalizing GPGPU came from academia. Ian Buck, a PhD student at Stanford University, led a team developing Brook GPU, a programming language that abstracted the complexity of the graphics pipeline. Brook allowed code to be written in a C-like syntax, which was then compiled down to the graphics primitives the GPU understood. Buck's work demonstrated that it was possible to expose the GPU as a streaming coprocessor without forcing the programmer to learn OpenGL or DirectX. NVIDIA recognized the potential of this research. In a move that foreshadowed their talent acquisition strategy, they hired Buck to lead their compute software strategy. The goal was to replace the hacks of GPGPU with a formal, supported architecture that treated the GPU as a legitimate computing device, not just a toy for gamers.
In 2006, NVIDIA launched the G80 architecture, GeForce 8800 GTX. It was a radical departure from all previous designs and arguably the most risky product launched since the Riva 128. The G80 discarded the fixed function pipeline entirely. Instead of separate vertex and pixel shaders, it featured a massive array of streaming multiprocessors, SMs, capable of executing any type of thread. If a game needed more geometry processing, the SMs acted as vertex shaders. If it needed complex lighting, they acted as pixel shaders. This unified shader architecture ensured that no silicon sat idle, dynamically balancing the load based on the specific needs of the application. 128 distinct shading units replaced the segregated vertex pixel pipelines. The architecture could handle multiple instructions across multiple data threads, a model NVIDIA termed SIMT. This allowed for much more complex control flow than previous SIMD, single instruction, multiple data designs. Unlike previous GPUs that used vector processing, operating on RGBA colors simultaneously, G80 used scalar processors. This was crucial for general computing, as scientific math often deals with individual scalar values rather than four-component vectors. The G80 was sold to gamers as the ultimate card for Crysis and Call of Duty, but hidden inside every GeForce 8800 was a supercomputer-class parallel processor waiting to be unlocked. This was NVIDIA's Trojan horse strategy. By bundling this advanced compute capability into consumer hardware, NVIDIA ensured that millions of CUDA-capable devices flooded the market overnight. Developers didn't need to buy a $10,000 workstation to learn parallel programming. They just needed the video card already in their gaming PC. This strategy was instrumental in building the initial developer base. While competitors like ATI, acquired by AMD, fragmented their approach with different architectures for gaming and compute, NVIDIA unified them. Every GeForce card was a Tesla development kit in disguise. This created a ubiquity that no other high-performance computing platform could match. Alongside the G80, NVIDIA released Cuda, Compute Unified Device Architecture, in November 2006. Cuda was the software key that unlocked the G80 hardware. It allowed developers to write C-like code that ran directly on the GPU, bypassing the arcane graphics APIs, OpenGL or DirectX, entirely. At the time, this was viewed by the industry as a quixotic money pit. ATI favored a more open but less polished approach, close to Metal and later OpenCL.
NVIDIA conversely insisted on a proprietary, vertically integrated stack. Critics argued that NVIDIA was investing billions in silicon features, caches, double precision support, and complex logic controllers that gamers didn't need and wouldn't pay for. The G80 and Cuda represented a fundamental shift in the relationship between hardware and software. Previously, hardware was designed for graphics and software had to adapt. With Cuda, NVIDIA began designing hardware for software, specifically for the paradigm of massive data parallelism.
The Wilderness Years, Building the Ecosystem, 2007-2012. Between the launch of Cuda in 2006 and the AI explosion of 2012, NVIDIA faced a period of intense skepticism. The gaming market was cyclical and maturing, and the compute market was minuscule. The stock price stagnated, and analysts frequently questioned the wisdom of spending die area on HPC, high-performance computing, features that increased power consumption and cost without an obvious return on the gaming market. However, during this period, NVIDIA was quietly laying the groundwork for its future dominance by cultivating centers of excellence and solving critical problems in niche scientific fields. This strategy involved deep collaboration with academic researchers and industry labs, effectively subsidizing their work in exchange for feedback on the architecture. While the world waited for a killer app for GPUs, 3 specific industries began to adopt Cuda, providing the crucial feedback loop that refined the architecture. These early adopters were not interested in AI. They were interested in simulation. One of the earliest successes was in molecular dynamics, MD. Simulating the interaction of atoms in a protein requires calculating the forces between every pair of atoms, an ON² problem that is massively parallelizable. Researchers like John Stone at the University of Illinois Urbana-Champaign, UIUC, and Axel Kollmeyer at Temple University began porting code to Cuda. The results were staggering. Software like VMD, Visual Molecular Dynamics, and Ampere saw speedups of 10x to 100x compared to CPUs. This proved that GPUs could do real science, not just theoretical demos. It led to the establishment of the first Cuda Center of Excellence at UIUC in 2008, directed by Win-Mei Hu. Hu's team literally wrote the textbook on parallel programming massively parallel processors, educating a generation of students who would later populate the AI labs of Google and Facebook. This academic seeding was deliberate. NVIDIA donated hardware and funded research grants, ensuring that the next generation of computer scientists grew up thinking in Cuda. Perhaps the most financially significant early adopter was the oil and gas industry. Exploration companies use seismic waves to map subsurface structures. The most accurate algorithm for imaging complex geology, like salt domes in the Gulf of Mexico, is reverse time migration, RTM. RTM involves solving the two-way wave equation forward and backward in time. On CPUs, a single survey could take months to process. In 2008-2009, companies like Schlumberger, Chevron, and Hess began deploying NVIDIA Tesla GPUs to run RTM. The speedups were transformative. Chevron reported seeing 12x to 15x improvements. This effectively subsidized the development of NVIDIA's Tesla line of data center cards. While gamers paid for the GeForce R&D, Big Oil paid for the enterprise reliability features, ECC memory, rack mount designs that would later be essential for AI. The revenue from these high-margin sales allowed NVIDIA to continue investing in compute features even when the consumer market was soft. Wall Street also took notice. Hanweck Associates, a financial analytics firm, used Cuda in 2008 to accelerate options pricing models. Derivatives pricing, often relying on Monte Carlo simulations, is a latency-sensitive task. Hanweck demonstrated that a few GPUs could replace racks of CPU servers, reducing both latency and cooling costs. This server consolidation narrative became NVIDIA's primary sales pitch to the enterprise market
long before AI arrived. Despite these niche successes, NVIDIA's financial situation was precarious. The investment in Cuda required massive R&D spending. Between 2008 and 2012, NVIDIA's stock price was often battered by macro factors, the 2008 financial crisis, and specific failures, the chip packaging defects in 2008 that cost them nearly $200 million. Investor sentiment was often hostile. Critics viewed the Tesla business unit as a distraction from the core gaming business and the emerging mobile market, Tegra. Jensen Huang, however, maintained the course, famously stating to employees and investors that accelerated computing was the inevitable future of Moore's Law. This period is retrospectively viewed as the bet the company era. Had AI not emerged, NVIDIA might have remained a niche gaming hardware vendor or been acquired. The wilderness years were characterized by a stubborn refusal to pivot back to pure graphics. Even as Intel pushed its Larrabee project, an attempt to use x86 cores for graphics, and AMD focused on integrating CPU and GPU, APUs, NVIDIA doubled down on the distinct nature of the GPU as a parallel processor.
The spark, ImageNet 2012 to 2014. By 2012, artificial intelligence was recovering from a decades-long winter. Neural networks, invented in the 1950s, were mathematically sound but computationally impractical. They required vast amounts of data and massive parallel processing power to train, neither of which existed in the 1990s. The prevailing wisdom in the AI community was that neural networks were a dead end, and that other methods like support vector machines, SVMs, were the future. The breakthrough came from the University of Toronto. Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton designed a deep convolutional neural network to compete in the ImageNet Large-Scale Visual Recognition Challenge, ILS-VRC. The team realized that CPUs were too slow to train their deep model. They turned to two NVIDIA GeForce GTX 580 GPUs. The choice was pragmatic. The GTX 580 was a consumer card, affordable and programmed via Cuda. The GTX 580 only had 3 GB of memory. The model, AlexNet, was too large to fit on one card. Krzyzewski wrote specialized Cuda kernels that allowed the model to be split across 2 GPUs, communicating directly. This forced model parallelism was a precursor to modern multi-GPU training. On September 30, 2012, AlexNet crushed the competition. It achieved a top 5 error rate of 15.3% compared to 26.2% for the second-place entry, which used traditional computer vision techniques. This margin of victory was so shocking that it effectively ended the debate over deep learning's viability. The academic community immediately pivoted. Within a year, almost every top entry in the ImageNet competition was using a GPU-accelerated neural network. Jensen Huang's reaction to AlexNet separates NVIDIA from other tech giants of the era. While Intel and Google viewed deep learning as a software curiosity, Huang recognized it as the killer app for the architecture he had spent 6 years building. In interviews, Huang recalled the moment researchers began reaching out for more powerful GPUs. NVIDIA immediately pivoted its software stack. They didn't just sell chips, they began optimizing the mathematical primitives required for neural networks. This led to the development of cuDNN, Cuda Deep Neural Network Library, a middleware layer that optimized convolution routines specifically for deep learning. The 2012 to 2014 period was characterized by a frantic repurposing of the roadmap. The Kepler architecture, 2012, was already out, but the Maxwell, 2014, and Pascal, 2016, were adjusted to prioritize the specific floating-point operations, FP16, FP32, that deep learning required, moving further away from pure graphics rendering requirements. Internal emails and communications from this era reveal a fundamental disconnect between NVIDIA sales teams and the new breed of AI customers. Sales teams used to selling to gamers or IT managers struggled to understand the needs of data scientists, who demanded massive throughput for training runs. This friction forced NVIDIA to retrain its entire workforce, shifting the culture from frames per second to floating-point operations per second.
The AI Factory, 2015 to 2020.
If the G80 was the Trojan horse, the Pascal P100, released in 2016, was the war machine. It was the first NVIDIA GPU designed explicitly with deep learning as a primary use case, not an afterthought. The introduction of NLink was particularly critical. It allowed GPUs to communicate with each other at speeds far exceeding the PCIe bus, effectively creating a single, massive logical GPU. This was essential for training the increasingly large models that were beginning to emerge. The launch of the Volta V100 in 2017 marked the definitive separation of compute GPUs from gaming GPUs. Volta introduced tensor cores, specialized execution units that performed one specific operation, multiplying two 4x4 matrices and adding a third, D equals A times B plus C. This operation is the fundamental mathematical building block of deep learning. By dedicating silicon area to this specific math, NVIDIA achieved performance gains that far outstripped Moore's law. While general-purpose CPUs struggled to double performance every 2 years, NVIDIA's Tensor Core-equipped GPUs were delivering 10x performance jumps for AI workloads. This performance disparity created a vacuum that no CPU vendor could fill. By 2018, NVIDIA's dominance was no longer just about hardware speed. It was about software inertia. The Cuda ecosystem had grown to millions of developers. Every major deep learning framework, TensorFlow, PyTorch, Caffe, was built on top of NVIDIA's cuDN libraries. Competitors like AMD and Intel struggled to break this lock-in. To use an AMD GPU, a researcher often had to rewrite code or use translation layers that were buggy and slow. To use NVIDIA, they simply ran pip install TensorFlow code. This "it just works" factor created a virtually insurmountable moat. The academic centers of excellence established a decade prior were now churning out PhDs who only knew how to think in CUDA. The cost of switching was not just hardware, it was the entire intellectual capital of the AI research community.
Global dominance and the Omniverse, 2020 to present. The 2020 launch of the Ampere A100 and the 2022 launch of the Hopper H100 cemented NVIDIA's role as the engine room of the modern economy. The H100, in particular, became the most sought-after commodity in the technology world during the generative AI boom of 2023 to 2024. These chips introduced transformer engines, specialized logic to accelerate the specific architecture behind models like GPT-4, Generative Pre-trained Transformer. This demonstrated NVIDIA's tight coupling with the software research community. As soon as a new model architecture, transformers, became dominant, NVIDIA baked support for it directly into the silicon. This responsiveness is a key competitive advantage. While other chip makers wait for standards to settle, NVIDIA implements them in silicon in near real time. A critical insight into modern NVIDIA is that it no longer sells just chips. It sells AI factories. The acquisition of Mellanox in 2020 for $7 billion was a strategic masterstroke, giving NVIDIA control over the high-speed networking Infiniband required to connect thousands of GPUs together. In the era of large language models, or LLMs, a single GPU is insufficient. Training runs require tens of thousands of GPUs working in concert. The bottleneck is often the network, not the compute. By owning Mellanox, NVIDIA ensures that its GPUs can communicate with minimal latency. With the introduction of the DGX systems and the Grace Blackwell superchips, NVIDIA now sells entire data centers as a product. They have effectively vertically integrated the entire supercomputing stack, from the transistor to the networking cable to the software compiler. By 2024, NVIDIA had become one of the most valuable companies on Earth. However, this ascent was not linear. The crypto hangover of 2018 and the post-COVID inventory correction of 2022 caused massive drawdowns in the stock price. These events highlight the inherent volatility of the semiconductor cycle, even for a dominant player. Yet, the demand for generative AI appears to be decoupling NVIDIA from traditional semiconductor cycles. The transition from computing as instruction execution, CPUs, to computing as data inference, GPUs represents a fundamental re-platforming of the global IT stack, a multi-trillion-dollar transition that NVIDIA currently monopolizes. The risks now are geopolitical, export controls to China, and competitive, like hyperscalers like Google and Amazon building their own chips. But the lead established by the Cuda ecosystem remains formidable. The era of the AI factory. The global technology landscape is currently undergoing a structural transformation comparable in magnitude to the Industrial Revolution or the advent of the Internet. This shift is driven by the emergence of generative artificial intelligence, AI, and large language models, or LLMs, technologies that have graduated from academic curiosities to central pillars of the global economy. At the epicenter of this seismic shift stands NVIDIA Corporation. No longer merely a manufacturer of graphics cards for gaming, NVIDIA has effectively become the utility provider for the AI age, building what its CEO, Jensen Huang, refers to as AI factories, data centers where the raw material is data and the output is intelligence. This part provides an exhaustive analysis of the hardware, software, and economic ecosystems that enable this dominance. The ascent of NVIDIA is not a story of accidental success. It is the result of a deliberate, decades-long architectural divergence from general-purpose computing toward accelerated computing. By pivoting its silicon philosophy from the scalar processing of central processing units, or CPUs, to the massive parallelization of graphics processing units, or GPUs, NVIDIA created the physical substrate upon which the modern AI revolution runs. The implications of this dominance extend far beyond silicon. The scarcity of NVIDIA's H100 and Blackwell GPUs has altered supply chain logistics, reshaped the balance of power in the semiconductor manufacturing sector, and triggered geopolitical friction between global superpowers. As nations and corporations race to secure sovereign AI capabilities, the possession of high-performance and video hardware has become a proxy for national competitiveness. This part dissects these dynamics, tracing the technical evolution from the Ampere architecture to the forthcoming Rubin platform, analyzing the impenetrable software moat of Cuda, and evaluating the fragile, high-stakes supply chain that underpins the entire AI economy. The architectural divergence, the physics of parallelism. To comprehend the necessity of NVIDIA's hardware, one must first understand the fundamental limitations of the traditional computing paradigm that preceded it. The AI explosion is, at its core, a victory of parallel processing over sequential execution. For decades, the Central Processing Unit, CPU, was the undisputed engine of computation. Its architecture is designed for versatility, complex logic branching, and low-latency execution of sequential tasks. A modern CPU is analogous to a master craftsman or a head chef. It is exceptionally skilled at handling a diverse array of complex, interdependent instructions. It utilizes sophisticated techniques such as out-of-order execution, branch prediction, and large caches to minimize the time it spends waiting for memory, ensuring that operating systems and varied applications run smoothly. However, the mathematical foundation of deep learning is fundamentally different from general-purpose computing. Neural networks, particularly the transformer models that power GPT-4 and Llama 3, rely on matrix multiplication, GEM, and vector addition on a massive scale. Training a model involves adjusting billions, sometimes trillions of parameters through a process of forward and backward propagation. This workload is not characterized by complex branching logic, but by brute force arithmetic. In this context, the CPU's strengths become liabilities. Its complex control units and large caches consume valuable silicon real estate that could otherwise be used for arithmetic logic units, ALUs. While CPUs possess single-instruction multiple data, SIMD capabilities, such as AVX 512, their parallelism is limited to vector units within a few dozen cores. For a workload requiring quintillions of floating-point operations, the CPU is inefficient, consuming excessive energy for the throughput it provides. The graphics processing unit, GPU, approaches computation with a diametrically opposite philosophy. Originally designed to render pixels on a screen, a task that requires calculating the color and lighting for millions of pixels simultaneously, the GPU is an engine of massive parallelism. Where a CPU might have 64 powerful cores, a GPU, like the NVIDIA H100, possesses tens of thousands of simpler cores optimized for throughput rather than latency. The GPU architecture excels at SIMD operations, where a single instruction, e.g. multiply, is applied simultaneously to vast arrays of data, e.g. neural network weights. This architecture is perfectly aligned with the mathematics of deep learning. When a neural network trains, it performs the same dot product operation across the entire matrix of weights. The GPU can process these massive grids of numbers in parallel, effectively hiding the latency of memory access by keeping thousands of threads active at once. If one group of threads is waiting for data from memory, the GPU instantly switches to another group that is ready to compute, masking the latency that would stall a CPU. This fundamental architectural advantage, the ability to trade single-thread latency for massive aggregate throughput, is the bedrock of the AI explosion. It turned the GPU from a gaming accessory into the engine of scientific discovery and artificial intelligence.
The Silicon Genealogy, from Ampere to Blackwell. NVIDIA's dominance is not static. It is maintained through a relentless cadence of architectural innovation. Each generation of NVIDIA data center GPUs has introduced specific hardware features tailored to the evolving needs of AI researchers, creating a virtuous cycle where hardware advances enable new model architectures, which in turn demand even more powerful hardware. Released in 2020, the NVIDIA A100 Tensor Core GPU, built on the Ampere architecture, laid the groundwork for the current generative AI boom. It was the primary hardware used to train OpenAI's GPT-4, a feat that required the coordinated power of approximately 20,000 to 25,000 A100 units running for months. The A100 introduced several critical innovations that bridged the gap between scientific computing, FP64, and AI training, FP16 or BF16. Unlike standard Cuda cores, tensor cores are specialized execution units designed specifically to perform matrix multiply accumulate operations in a single clock cycle. The A100's tensor cores introduce support for TF32, a hybrid precision format. TF32 uses the same 10-bit mantissa as FP16 for speed, but retains the 8-bit exponent of FP32 for dynamic range. This allowed researchers to achieve FP32-like stability and training with the throughput advantages of lower precision without requiring any code changes. The A100 hardware supports fine-grained structured sparsity, which can double the throughput of tensor operations by skipping calculations on zero-valued weights in the neural network. The A100 offered a peak throughput of 312 TFLOPS for FP32 tensor operations and provided 80 gigabytes of HBM2E memory with bandwidths exceeding 2 terabytes per second. This memory bandwidth was crucial as AI models were growing larger than the cache of any single chip, making the speed at which data could be moved into the compute units the primary bottleneck. If the A100 built the foundation, the H100, Hopper architecture, released in 2022, was the accelerant. The H100 was explicitly designed with the transformer model architecture in mind, the T in GPT. The defining feature of the H100 is the transformer engine, a combination of hardware and software that dynamically manages calculation precision. The engine intelligently analyzes the statistics of the tensors, data arrays, flowing through the neural network layers. It automatically determines if a layer can be computed in FP8, 8-bit floating point, without sacrificing the final accuracy of the model. If high precision is needed, it defaults to FP16, if not, it downcasts to FP8. FP8 math is twice as fast as FP16 and consumes half the memory bandwidth. By enabling FP8 training, the H100 delivers up to 9 times faster AI training and 30 times faster inference for large language models compared to the A100. In practical applications,
Training a 7 billion parameter GPT model on H100s using FP8 was found to be 3 times faster than on A100s using BF16 with no degradation and convergence. H100 also introduced the 4th generation of NVLink, boosting GPU to GPU interconnect bandwidth to 900 gigabytes per second, a 7x increase over standard PCIe Gen 5. This bandwidth is critical for model parallelism. Where a single trillion parameter model is split across hundreds of GPUs, the interconnect ensures that the GPUs can exchange parameters fast enough to act as a single, unified computer.
Introduced in 2024, the Blackwell architecture represents NVIDIA's response to the physical limits of semiconductor manufacturing. As transistors shrank to the nanometer scale, NVIDIA hit the reticle limit, the maximum physical size of a chip that can be printed by a lithography machine, roughly 800 millimeters squared. To continue scaling performance, NVIDIA moved to a chiplet architecture. The B200 is not a single silicon die. It is 2 massive dies packaged together on a single substrate. They are connected by a proprietary 10 terabytes per second chip-to-chip interconnect, NVHBI. This connection is so fast and low latency that the software treats the 2 dies as a single logical GPU. This allows the B200 to pack 208 billion transistors, more than 2.5 times the transistor count of the H100. Blackwell introduces the 5th generation Tensor Core, which supports FP4, 4-bit floating point precision. Reducing precision to 4 bits drastically reduces the memory footprint and energy required for calculations. Theoretically, FP4 offers double the throughput of FP8. To prevent the massive loss of accuracy inherent in using only 4 bits of data, Blackwell uses a technique called micro-tensor scaling. This involves fine-grained management of scaling factors for small blocks of data, allowing the hardware to maintain high dynamic range even at extremely low precision. The result is a staggering leap in performance. For training massive models, e.g., a 1.8 trillion parameter mixture of experts model, the Blackwell architecture delivers a 30x speedup and 25x better energy efficiency compared to the Hopper generation. This efficiency is critical. Without it, the power demands of next-generation AI data centers would become economically and environmentally unsustainable.
The interconnect fabric. Why the data center is the computer. A single GPU, no matter how powerful, cannot train a frontier AI model. Models like GPT-4 or Grok require tens of thousands of GPUs working in unison. This necessity shifts the engineering challenge from the chip level to the data center level. NVIDIA's dominance is partly due to its proprietary networking technologies, which allow it to sell entire supercomputers rather than just components. Standard data center networking, Ethernet or PCIe, is too slow and has too high latency for the all-to-all communication patterns of deep learning. When a model is split across GPUs, the chips must constantly exchange gradients, partial updates to the model weights. If this exchange is slow, the powerful GPUs sit idle. NVIDIA developed NVLink, a high-speed proprietary interconnect that bypasses PCIe. In the Hopper generation, NVLink provides 900 gigabytes per second of bidirectional bandwidth per GPU. To scale this beyond a single server, NVIDIA uses NVSwitch, a physical switch chip that connects multiple NVLinks. In the Blackwell era, NVIDIA introduced the GB200 NV72, a rack-scale system where 72 GPUs are connected via a massive copper spine acting as a single NV switch domain. This allows all 72 GPUs to communicate with each other at 1.8 Tbps, effectively functioning as a single GPU with exaflops of compute and terabytes of unified memory. while NVLink handles communication within a rack or pod. Connecting thousands of racks requires Ethernet or Infiniband. Traditional Ethernet is designed for lossy traffic. If a packet is dropped, it is resent. In AI training, a dropped packet can stall the entire training run. To address this, NVIDIA introduced the Spectrum-X Ethernet platform. Used in the xAI Colossus cluster, Spectrum-X is optimized for AI workloads. Control. It utilizes adaptive routing and congestion control to prevent packet collisions. In the xAI cluster, Spectrum-X achieved 95% data throughput efficiency compared to the roughly 60% efficiency typical of standard Ethernet in high-load scenarios. This innovation allows massive clusters to use standard Ethernet cabling while approaching the performance of specialized InfiniBand networks.
The Cuda ecosystem and developer inertia. Cuda allows developers to program GPUs using C++, unlocking their parallel processing power for general-purpose tasks. Over nearly 2 decades, NVIDIA has cultivated a massive library of optimized mathematical kernels like QBLAS and QDNN that are hyper-tuned for their hardware. Competitors like AMD with ROCm and Intel with 1API must not only build chips that match NVIDIA's flops, but also provide a software stack that runs existing AI codebases seamlessly. Because most deep learning frameworks like PyTorch and TensorFlow are built on top of CUDA primitives, porting them to other architectures often results in performance degradation or bugs. Even if a competitor's chip has higher theoretical performance, NVIDIA GPUs often achieve better real-world performance because the CUDA kernels optimize memory access patterns and thread utilization better than the less mature compilers of competitors. As the AI market matures, the focus is shifting from training, creating the model, to inference, running the model for users. Efficiency here translates directly to profit margins. A fierce battle for optimization supremacy is playing out between open-source solutions and NVIDIA's proprietary tools. One of the most significant breakthroughs in inference efficiency was the introduction of paged attention implemented in the open-source library VLLM. During inference, the KV cache, or key-value cache, stores the context of the conversation. Traditional systems allocated contiguous memory blocks for this cache, leading to massive fragmentation and wasted memory, similar to the internal fragmentation problem in OS memory management. Paged attention breaks the KV cache into non-contiguous blocks, or pages, allowing the GPU to use memory far more flexibly. This enables continuous batching, or in-flight batching, where the GPU processes multiple requests simultaneously, evicting completed tokens and inserting new ones dynamically. This can double or triple the throughput of the server. NVIDIA responded with TensorRT LLM, a highly optimized inference library. TensorRT LLM incorporated in-flight batching and optimized it further using proprietary knowledge of the hardware. It compiles the model into a highly efficient executable, fusing layers to reduce memory bandwidth pressure. While VLLM is favored for its flexibility and ease of use, TensorRT LLM generally holds the crown for peak throughput on NVIDIA hardware H100, B100, offering deeper optimizations for FP8 and FP4 quantization that open-source libraries struggle to match immediately. Benchmark data suggests TensorRT LLM provides superior throughput at high batch sizes, while VLLM often wins on latency and ease of deployment for smaller concurrent loads.
A potential threat to the CUDA moat is OpenAI Triton, an open-source language that allows developers to write high-performance GPU kernels without the deep complexity of CUDA. Triton acts as an abstraction layer. If it becomes the standard, code could theoretically run as efficiently on AMD or Intel chips as on NVIDIA chips, eroding the CUDA lock-in. However, currently, Triton's backend is most optimized for NVIDIA GPUs, ironically reinforcing NVIDIA's performance lead in the short term. Manufacturing and supply chain, the CoWoS bottleneck. The defining constraint of the AI boom has not been the ability to design chips, but the ability to package them. NVIDIA is a fabless company. It relies on TSMC, Taiwan Semiconductor Manufacturing Company, for production. The H100 and B200 are not simple chips. They use chip-on-wafer-on-substrate, CoWoS, advanced packaging. CoWoS involves placing the GPU logic die and the HBM memory stacks side by side on a silicon interposer. This interposer contains microscopic wiring, TSVs, through silicon vias that connects the memory to the GPU at incredibly high speeds. Creating this interposer is a slow, high-precision process. In 2023, TSMC's CoWoS capacity was the primary bottleneck limiting H100 supply. Demand outstripped supply by such a magnitude that NVIDIA reportedly booked 40 to 70% of TSMC's total CoWoS capacity for 2024 and 2025. In response, TSMC aggressively expanded CoWoS capacity, aiming to double output from 8,000 wafers per month in early 2023 to over 16,000 by the end of 2024. The other critical component is HBM, high bandwidth memory. Unlike the GDDR memory in gaming cards, HBM stacks DRAM dies vertically. The A100 used HBM2E. The H100 moved to HBM3. The B200 utilizes HBM3E, which pushes bandwidth to 8 terabytes per second per GPU. This memory is primarily supplied by SK Hynix, which has led the market in HBM3E production, followed by Samsung and Micron. Recognizing the geopolitical risk of having the entire AI supply chain centered in Taiwan, NVIDIA has begun diversifying. In a historic milestone, NVIDIA and TSMC celebrated the first production of Blackwell wafers at TSMC's Fab 21 in Arizona. This represents a critical step toward onshoring the production of strategic AI assets. NVIDIA is also duplicating its back-end supply chain, the packaging and testing steps, in the United States through partnerships with Ampere, creating redundancy against a potential blockade or conflict in the Taiwan Strait. The economics of AI, the data center revenue flip. The AI explosion has fundamentally rewritten NVIDIA's financial DNA. For most of its history, NVIDIA was a gaming company that dabbled in professional visualization and data centers. In the last 3 years, this dynamic has inverted. The release of the H100 triggered an unprecedented capital expenditure, CapEx, cycle among hyperscalers, Microsoft, Meta, Google, Amazon. In fiscal year 2025, NVIDIA's data center revenue reached $115.19 billion, a staggering 142% increase year over year. In comparison, the gaming segment revenue was $11.35 billion, representing only 8.7% of total revenue. Just a few years prior, gaming was the majority revenue source. Data center revenue now accounts for nearly 90% of the company's total intake. NVIDIA has effectively transformed from a consumer electronics component supplier to the most valuable infrastructure company in the world. The economics of buying NVIDIA GPUs are driven by total cost of ownership, TCO. While an H100 GPU costs upwards of $25,000, $30,000, the performance per watt and performance per dollar for AI workloads justify the expense. NVIDIA argues that upgrading to Blackwell provides such massive efficiency gains, 25x lower energy cost for large models, that the hardware effectively pays for itself by reducing the electricity bill and the number of servers required. In the inference market, the key metric is joules per token. By moving to FP4 precision on Blackwell, NVIDIA aims to drive this metric down, making it economically viable to deploy LLMs into everyday applications where margin sensitivity is high.
Real-world impact. The rise of the Gigafactory.
The theoretical flops of NVIDIA chips have materialized into some of the largest engineering projects in human history. Elon Musk's xAI built the CoWoS cluster in Memphis, Tennessee, setting a benchmark for speed and scale. The cluster consists of 100,000 NVIDIA H100 GPUs with a roadmap to expand to 200,000. This singular cluster represents billions of dollars in hardware. The facility was brought online in just 122 days, a process that typically takes 12 to 24 months for legacy data centers. This speed was achieved through tight integration of NVIDIA's Spectrum-X networking and Supermicro's liquid-cooled rack designs. CoWoS is training the Grok 3 models. The use of Spectrum-X Ethernet allowed xAI to utilize standard Ethernet cabling while achieving near InfiniBand performance, simplifying the supply chain for cabling and switches. Meta, Facebook, has taken a different approach, committing to open-source AI, Llama, powered by massive proprietary infrastructure. Meta announced plans to acquire 350,000 H100 GPUs by the end of 2024, bringing their total compute inventory to an equivalent of 600,000 H100s. The Llama 3 models were trained on clusters of 24,576 H100 GPUs. The sheer scale of this compute allows Meta to train models on trillions of tokens of data, achieving state-of-the-art performance that rivals closed models like GPT-4.
NVIDIA's hardware is now considered a dual-use technology, capable of powering both economic growth and advanced military systems. This has placed the company at the center of the U.S.-China trade war. The U.S. government has imposed export controls, preventing the sale of advanced GPUs, A100, H100, B200 to China. The controls set a limit on the performance density of chips that can be exported. To comply, NVIDIA designed the H20 GPU. It offers high memory bandwidth, essential for inference, but has its peak compute performance artificially throttled to fall into the green zone of permissible exports. Despite the H20, NVIDIA's revenue from China has suffered. The company reported a $4.5 billion charge related to H20 inventory adjustments as domestic Chinese competition intensified. The vacuum left by NVIDIA in China has fueled the rise of Huawei. Huawei's Ascend 910B chip has emerged as a viable alternative to the A100 H20 for Chinese firms. While it lags behind the H100 in raw performance, its Interconnect technology, HCCS, allows for clustering, and its software stack, CANN, is maturing. Reports suggest the Ascend 920, targeting 2025, aims to compete with the H100, utilizing HBM3 memory and 900-plus teraflops performance. This suggests that U.S. sanctions may have delayed but not stopped China's AI progress. Beyond China, nations are racing to secure sovereign AI, domestic infrastructure controlled by the state. NVIDIA has signed major deals with Saudi Arabia via the UMAIN initiative and the UAE to build AI factories. The U.S. government now requires licenses for these sales to prevent chips from being diverted to China, highlighting the strategic nature of the hardware. France and the UK are also investing heavily in sovereign clusters to ensure they are not entirely dependent on U.S. hyperscalers for their AI capabilities.
Future roadmap: Rubin and the limits of physics. As the industry deploys Blackwell, NVIDIA is already preparing its successor, the Rubin architecture, R100, scheduled for 2026. Rubin will focus on overcoming the memory wall, the fact that memory bandwidth is growing slower than compute speed. Rubin is expected to debut HBM4 memory. This next-generation memory will feature a doubled channel width and, crucially, logic stacking. This means the base layer of the memory stack will be a logic chip, potentially allowing the memory to perform some computation itself, near memory processing, drastically reducing the energy cost of moving data.
Rubin will be paired with the Vera CPU, an ARM-based successor to the Grace CPU, featuring optimized cores for data handling. With Blackwell already pushing racks to 120 kilowatts, Rubin will likely require liquid cooling as a mandatory standard. The era of air-cooled data centers for frontier AI is effectively over. NVIDIA's journey from a graphics card manufacturer to the cornerstone of the AI economy is a case study in technological convergence. By recognizing early that the parallel processing needs of graphics were mathematically identical to the needs of deep learning, NVIDIA prepared the physical ground for the AI explosion. Through the A100, H100, and Blackwell architectures, NVIDIA did not just make chips faster, they fundamentally altered the architecture of the data center, turning racks of silicon into unified AI factories. Their mastery of the supply chain, navigating the CoWoS bottleneck and the transition to HBM, and their construction of an impregnable software moat with Cuda have made them nearly indispensable. However, challenges loom. The physical limits of power and heat, the geopolitical fracture of the global semiconductor market, and the rise of determined competitors like Huawei and open standards like Triton ensure that NVIDIA's continued dominance is not guaranteed. Yet, as of 2025, the reality remains: the AI revolution is running on NVIDIA silicon.